Hello everyone, my name is Ayush. Today, me and my partner Ambar will be presenting the Big Data for Health Reproducibility Challenge. Our goal is to use admission clinical notes and diagnostic codes in order to predict the clinical trajectory of patients, specifically for three problems: disease prediction, mortality prediction, and readmission prediction. This problem is very challenging because of the characteristics of clinical notes themselves. They have a lot of free text, they're granular, and they're full of ambiguities and redundancies. Current state-of-the-art models, they either work on simpler problems or are very complex and do not generalize well across hospitals. We selected a paper which aligns well to the solution for this problem and is published not too long back in 2021. On a high level, the paper proposes to pre-process data in this way, using phenotyping to extract UMLS concepts, use threshold criteria to control information, and model the prediction learning on rich phenotype information. The key contribution of this paper is to come up with a richer set of phenotypes, which we can control based on a similarity threshold of values during CUI concept extraction, and also by applying domain knowledge using predetermined TUIs in order to limit these CUIs even further in order to properly match the problem context. The paper has several claims, but the most important one is that proper tuning of similarity threshold parameters and TUIs will give better results on patient trajectory problems. The experiments in this paper, they are very computationally heavy. Hence, in order to determine the good scope overall for our reproducibility challenge, we have different problems that are in scope and out of scope, as claimed by the paper. Our focus overall, though, has been to reproduce trends rather than replicate exact results. Okay.
So similar to paper, we use the MIMIC3 database, specifically admission diagnostics and admission clinical notes data. We used UMLS and quick UMLS software to extract the CUIs from pre-processed clinical notes. We used clinician validated TUIs for fitting CUIs to problem context, which we took from the paper. For experiments, we split data into 80-20, with 20% put aside for testing. Remaining 80% is used for training. Some initial analysis generated these statistics. Distribution of number of patients with respect to number of admissions shows that most of the patients have single admission, with patients having up to 26 admissions. Distribution of number of admissions with respect to number of diagnosis codes shows that around 13,000 patients have 9 ICD codes each. ICD codes are labels for disease prediction problems to determine the diagnosis of next admission. In data pre-processing, several steps are performed. Heavy pre-processing is applied to notes data to make it ready for UMLS UI's extraction. For example, all text is lowered. We removed anonymized text, extra spaces, time, special characters, etc. Then UMLS extracted CUIs are mapped to one hard vector per patient. Based on similarity threshold and TUIs list, 4 data sets are created. Data has around 7,000 diagnosis codes as ICDs, which is too high to generate an output from a neural network. It causes numerical instability while learning, hence these are mapped to 289 unique CCS codes. This is empirically proven to be beneficial in several applications without losing information. Moreover, we only need patients with multiple admissions and having clinical notes. After applying filter, we have 7,000 patients data, which is used for learning. We mainly experimented with the FFN model and basic model, which worked well according to paper. In general, we used alpha TUIs and 0.9 similarity threshold, which corresponds to set C in the paper. FFN model considers only last admission to predict for next admission. Architecture is very simple, with an input layer, one hidden layer, and an output layer. We use combined CUIs and CCS as input for all experiments, hidden size of 10,000, and output layer of depending on the problem. For disease prediction, we compared the actual next admission diagnosis with model predicted next admission diagnosis. We used binary cross entropy, loss function with sigmoid logits for backprop learning from loss. For picking the best model, we used 5-fold cross-validation. Because of processing power constraints, we trained the best model to 2,000 epochs instead of 5,000 epochs and saved the model which gives the lowest average ROC and low loss. Eventually, we loaded this model to evaluate on 20% of the test data. We also experimented with RNN architecture, it considers the whole admission history to predict the next admission.
All right, now on for the results. For the feed-forward network for disease prediction, the cross-validation curve shows both the training and validation loss converging and reducing with the number of epochs. We calculate statistics across epochs and fivefolds in order to calculate an average and determine the best model to train on. Training the best model for the feed-forward network for disease prediction on the whole training dataset produces a very nice loss curve over 2,000 epochs, and here are the statistics overall. For the RNN for disease prediction as well, it performs well. The cross-validation loss curves are shown here, and they converge well and reduce with the number of epochs. In this case, we trained the best model for 250 epochs with the complete dataset, and the trained model performed close to the findings of the original paper, which trained for 1,500 epochs. Here are the results now for mortality prediction for the feed-forward network. They're very encouraging, and the results align with the paper's findings. Again, for the RNN model, for mortality prediction, the results align with the paper's predictions and results. And we also tested readmission as well, and those results are available in our notebook as well as the GitHub. Comparing results across compared to the paper for both our FFN and RNN shows that we are able to achieve AU-ROC comparable to the paper. This performance is trending to get better with the number of epochs in terms of precision and recall as well. We also compared the number with combined versus single CCS plus CUI, and it's comparable to the paper. And disease prediction overall compares with the state-of-the-art models and the original paper's experiments.
Reproducing this paper was full of fun with its own challenges. Specifically, pre-processing work and UMLS extraction was tricky. There were long training times. Fortunately, the simple architecture worked with limited number of parameters. We also observed that while the author claims 80% of the data is used for training based on the code base, whole data is being used for cross-validation. In conclusion, this paper is reproducible, but requires a lot of processing. We could reproduce all pre-processing steps. For FFN and RNN disease problems, we could reproduce the trends and get closer to paper numbers with lower numbers of epochs, but we did not replicate the result in absence of more processing time. Mortality and readmission prediction are also reproducible. We also identified future work for additional experiments such as single input, optimizing learning rates, and using different architectures such as LSTM. With that, we want to thank you, the teaching staff and fellow students, for their guidance and support. Thank you.